Swayam Prabha. Digital India. Educated India.
So we're going to do one more thing before we take this whole thing down. We're going to see what would happen if we put a chiral center on this molecule. Start with a chiral molecule. We started with an asymmetric molecule. Now with this one symmetric, let's start with a chiral molecule. I mean, you could have 1 or 2 or 3 chiral centers, but just let's put one here. Let's say one of this is just a methyl. It could be an ethyl, purple, whatever, as a R group, or a hydroxyl, or any other group that won't interfere with these reagents. And so let's say we have a chiral center there. This is going to be 1, 2, 3. That's going to be an S for you. And let's see what's that going to do here. So I could even draw this as a wedge, or I could draw a line up if it's a Hayward projection. And I'm going to do just that. So since this is drawn as a Hayward projection, over here on the carbon right next to this terminal, you have a R group going up. And as I said, it doesn't have to be methyl, but let's say it is. What is that going to give you? What do you think? Is that chiral or achiral? First of all, it is going to be chiral because it doesn't have a plane of symmetry. If it is chiral, then what are the possibilities? You could have enantiomers, diastereomers, meso, and so on. In this case, these two are flipped, but this is not. So when you have some of the stereocenters flipped and some remaining the same, and even if it's one remaining the same and all the others are flipped, they cannot be enantiomers because they are not mirror images. If I take this, if I draw a mirror image of this methyl should be down. But the methyl cannot be moved because it comes fixed in that position up. So therefore, this is going to be non-superimposable stereoisomers here, and they are not enantiomers. So that by definition is going to be the D word, diastereomers. And the diastereomers would be in a 1-to-1 ratio. Now, we don't call this a raceme because the properties of this, like the boiling point, melting point, density, and so on, would be different for this compared to this. And even the optical rotation, we cannot predict. They will be different, but they won't be opposite and equal like in an enantiomer. This is going to have some value, and this is going to have some value, and we don't know what the relationship to those values are. So these are diastereomers. Each molecule by itself is chiral because it doesn't have a mirror plane of symmetry, but they are not mirror images. So therefore, you get a 1-to-1 diastereomer. Let's check this out. Same deal as before. Put your methyl groups going up. What do you think? Are they enantiomers, diastereomers, meso, same compound, identical, constitutional isomers? So many possibilities. Well, they're not constitutional isomers because they're all connected to the same things in the same places. So they're both stereoisomers. Same deal as before. These two are reflected, but this one is the same. It's fixed. Can't move it. So therefore, these are not mirror images, and they are stereoisomers, and that are not enantiomers. So those are, by definition, diastereomers. Again, you get a 1-to-1 mixture. Same deal here, guys. Once you get this, one of them, you can see it's the same thing over and over again. The relationship between these two, again, these are flipped. This is not flipped. Therefore, they are diastereomers. And here too, you have the same thing. Let's put our methyl group up, up, up. And you can see these are flipped, and this is not diastereomers. What about these? Well, these are achiral. What if you put one of these here? Now, the whole thing is going to be switched. The whole thing now changes because now these are chiral. And if you take them, you cannot reflect this onto this. They're not mirror images. And they're also non-superimposable. So they're not enantiomers, and they're not achiral, they are chiral. And one of them is reflected, one of them is the same. So therefore, these are also diastereomers. Let's look at this. Again, put your methyl groups up, 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 and same deal as before. These two are flipped, and one of them is not flipped, and so they are not mirror images. They're stereoisomers, and by definition, stereoisomers that are not mirror images are diastereomers. We went over that like 1,000 times only. All right, let's look at this one. Same here. Methyl up, up, up. These are reflected. This is not. So you can see a trend when you start with a chiral center. Now, same over here. You have a methyl group, and here's a methyl. In this case, your hydroxyl can go here or here. So you would get an additional molecule here, but there won't be any rearrangement because of the mercury holding on to both ends. So here too, your methyl is going to be up, and your hydroxyl can be up or down because there's an equal opportunity to attack here or here. So I'm just going to put OH up and down here, and OH up and down here, and let's draw them all out. So here's another one where you can have your OH down and methyl up here, or you could have the OH up here. So you can have 4 different compounds here. And look at this and tell me, what is the relationship between all of these? None of them is really like a major compound. And we can have 4 different ones. And in all of them, the methyl stereochemistry does not change. The hydroxyl can go up or down, and both of these are going to be diastereomers. So let's look at the relationship between this and this. Is there any relationship? Are they close cousins? Not really. Here the hydroxyl is 2 carbons away from that methyl, and here the hydroxyl is on the carbon right next to the methyl. So they're not stereoisomers. If it's a stereoisomer, all of the substituents would be in the same places, except they will have different spatial orientation. Here, it's not just a spatial orientation, it's a position shift. So therefore, these two are constitutional isomers. I'm going to call them CI, constitutional isomers. Now over here, if you take both of these, same here, both of these are also going to be constitutional isomers because you have a position shift. But if I take this and this, well, all the things are connected to the same carbons. But over here, just one of them is flipped, one of them is the same. So they are stereoisomers, but they're not mirror images because they are diastereomers. Stereoisomers that are not mirror images are by definition diastereomers. This and this, they're connected to the same things. However, this one and this one have one of them in the same direction and the other one is flipped. So these are 2 diastereomers. So we'd have absolutely no enantiomers. We got 4 diastereomers. So that's a little different here. Let's look at the protonation here and Markovnikov additions with acids. We got 2 examples, 1, 2, and this one too is a Markovnikov addition in the presence of acid. Let's look at these 2 and see, how they're different or are they the same. Let's look at it. So your H can attack, and well, let's not forget the methyl here, and I'm going to put that over here right now. Well, you can have a positive here or here, but let's see what happens if you have a positive form here with the hydrogen going to the carbon next door. What can this do? Is it going to get slam bam attacked by the chloride or bromide or iodide? What do you think? Well, look at it carefully. This is a secondary, and secondaries a bit unhappy, and especially if they see a neighbor who's kind of happier than them, they're a tertiary. So they're going to grab that hydrogen here from the tertiary center and pull it down. And so that's going to then give you a tertiary carbocation. And so now you have two hydrogens here. Rolls over with the hydrogen, and we did this before. And here is a positive charge now on the carbon that has the methyl group. So that's flat now. What's the next step? Well, now that you have a stable carbocation, it's not going to go anywhere because it's kind of happy here. It's a tertiary, and yippee, you're going to stay here as long as I can before it gets slammed by one of these. Let's say it's a bromide. You can get bromide up or down. So you're going to get your bromide attacking that above or below. Does it really matter? Let's look at it. You're going to get a bromide attacking, let's say, down and up. And in this case, both of them are identical because this is an achiral molecule. You have a planar symmetry right through there, right through here on the vertical plane. So therefore, this is going to be achiral. So you can't really jump to conclusions and say, oh, if it's an acid, it's going to be achiral. Look at this. You got diastereomers, and they're all chiral. And here, acid without the mercury, and so now you get rearrangement and achiral. All right, so you really have to look at each scenario here, case by case. All right, let's look at H2SO4 and water. What do you think? Is it going to be any different? Again, you're going to pull off that pi bond with a hydrogen, get a positive either here or here. And this can roll over, and this would be your major product. And for all of them, we are writing major products. So here's your water that's going to attack above and below. Am I right? Now you're going to have a migration here or a rearrangement of that going over here, and then getting a positive right here, attacked by water up and down. Deprotonation, and you know the whole story, just like in your SN1, and you're going to get OH2. H2O can attack up and down, and really doesn't matter which direction the water attacks because your final product is achiral. You got a planar symmetry right through there. So again, achiral. Hydrogen platinum. Well, what do you think? Your methyls here, methyls here. Is this chiral, achiral, enantiomers, diastereomers? What do you think, guys? Oh, you got a planar symmetry right through there. So this is the exact same molecule as that, and they are achiral. And they're both identical, so I'm just going to say identical as well. They're the same. What about this? You're going to have a chiral center here. That's not going to go anywhere. And so it will be chiral. This is your major product here, but you don't get enantiomers. All right, let's look at this guy. Again, methyls are up, up, and these are both pretty much identical, and we can do them both together. Two flipped, but one is the same. That's a typical example of a diastereomer. They're not mirror images, but they're stereoisomers. Everything's in the same place. So this is a diastereomer pair, and this is also a diastereomer pair. All right, guys, so that pretty much covers the whole gamut of reactions possible on the cyclopentane, with achiral, chiral, asymmetric, and symmetric. We may come back and do a long chain and see if you are going to have the same thing all over again. We'll see you soon. Talk to you guys later. And also make some flashcards, guys, with a mechanism on one side, reaction on the other. And let's say you're having insomnia or drank too much coffee, just keep looking at them. You automatically fall asleep. Okay, so see you soon. Bye.